Thanks, everyone. It's really an honor and a pleasure to be here once again. Also, just in case someone missed before, someone is missing an iPhone. So if you are missing an iPhone, then go talk to the tech guys over there and describe it. One hint, it's not pink or yellow, so you have to do a better job. I'm Trent. It's really a pleasure to be here. Today, I will be talking about yet a different topic than I talked about last year, which is yet a different topic than the year before. 2 years ago, I was talking about Moore's Law and machine learning and semiconductors. Last year, I was talking about ownership on the internet. This year, I'm talking about something, you know, some people might think is more mundane, but it's also super cool, and I don't think it's mundane at all, and that's databases. The common thread from this and last year is blockchains, and I'll just get started. So, this is probably a very elementary picture for most of you. You know, if you think about what are the elements of computing, there's really three things. There's processing, there's storage, there's communication. And if you were to sort of drill into that some more and think about how that translates to modern application stacks, you'd probably say, okay, well, storage breaks into two things. You've got the file system, and you've got the database. The file system is organized by hierarchies of directories and files. The database, you know, the UX is really about queryability. And under the hood too, the hierarchy is really, the file system is really more partition tolerant, whereas the database aims for consistency, sort of in the CAP theorem sense. And on the side, you know, the communications is just kind of there and the protocols that connect, and you have applications on top. Very straightforward, no problem, no problem. And how this manifests itself into modern stacks, this is an example of the cloud stack. And at the top level, you've got applications, whether they're web-based or mobile-based, Facebook, Netflix, Google Maps, that sort of thing. One level down, they're on different sorts of platforms, cloud platforms like AWS or Azure. And those platforms hold a few elements, the processing, the file system, and the database, or databases. So in the Amazon stack, you've got EC2 for the processing. For the file system side, you've got things like S3 for buckets, for blobs of media and so on, maybe a Google Drive. And then for databases, you've got things like MySQL and other SQL-style databases, or MongoDB and other NoSQL databases. So straightforward, straightforward. This is all dead obvious to you guys, I'm sure. Well, you know, there's this whole other universe that's been emerging for about 5 years now, starting with Bitcoin. And Bitcoin, the paper was released in late 2009. The software came out in early 2010. And very quickly it got the label of magic internet money. And people had a tough time putting their finger on what exactly it was. Even to this day, is it money? Is it an asset? Is it just some, you know, weird crypto-anarchist dream? What the heck is it? And, you know, different things have emerged over time. You know, there's been a lot of hype and a lot of technology developed. And one of the things that's happened is it actually really sparked a revolution. And that revolution was people realizing that the ideas of Bitcoin, the idea that you could have scarcity of something electronic, you could actually apply that not to just the traditional idea of e-cash, but to other things as well. So you could say, okay, what about other digital assets? What about digital art? What if I could own digital art the way that I own Bitcoin? And this is actually where Ascribe kind of came from. You know, my company started about 3 years ago, work on it 3 years ago. Or what about diamonds? Which isn't digital, but it's something that you can still track with supply chains, right? We were just having a conversation, what about used cars, right? If you had a much better trail of the ownership of the cars on a database that no one owns or controls, that's pretty powerful. So Bitcoin sparked this revolution. It morphed into the blockchain revolution, which was, I'll get into that more later, but a blockchain is really just a type of storage mechanism. And more recently, we've seen things like smart contracts, and most recently, DAOs, especially the DAO. And if you guys haven't seen this, I encourage you to check it out. It has raised more than $150 million as a crowdfunding, and it's still barely halfway through its fundraise. And the creators of the DAO are here in Berlin. So pretty interesting. There's some crazy things happening. It's really rewiring the internet for computing. I'll get more into that too. So basically, Bitcoin sparked this revolution. But Bitcoin itself and all of the other blockchain technologies basically have had a problem. Scale. Bitcoin has a theoretical max of 7 transactions per second. And actually, when you start to go past about 1.5 transactions per second, the network backs up, and it takes about 24 hours for a transaction to go through. They call Bitcoin blockchain bloated, yet it only holds 50 gigabytes. I can hold more on my thumb drive. Yet people talk about the idea of Bitcoin and these other networks as, these planetary databases. Well, do you know of any planetary databases that are smaller than your thumb drive? Not a very good planetary database, if you ask me. So that's a challenge, right? What about planetary scale? Is there some way to reconcile the dreams of blockchains with scale, the technology that we need to achieve these dreams? And you might ask, well, is there other places that have planetary scale? And you guys, a lot of you guys come from the big data world, so the obvious answer is yes, but I'll just start with an example, Netflix. Netflix uses 37% of the bandwidth of the internet, at least in the USA. That's pretty good. I'd say that's probably planetary scale usage, given the, the usage of the internet today. That's pretty good. What's under the core of Netflix? It's, well, big data, in particular the Cassandra databases, actually instances that they're running there. So Cassandra databases are actually powering Netflix to serve up this media. And this is an interesting plot here. What it is the x-axis is the number of nodes. The y-axis is the number of writes per second. And the first thing you can see is, well, on the x-axis, there's more than one node, right? There's more than one machine being used to serve up this data. It starts with, 50 on the left, all the way up to 350 on the right. And with 50 nodes, Netflix the Cassandra instances are running at 200,000 writes per second. And as you increase the number of nodes, as they increased, going from 50 to 150, and more, the number of writes per second increased correspondingly in a linear fashion. And if you think about it, that's actually pretty cool, right? It means, well, it's linear scaling, and it's actually able to swallow more and more and more data. And the core idea there, of course, is that the data itself, no single node is storing all the data. It's actually being sharded up. So each node is storing a subset. And then when the data is getting written, each node only has responsibility to keep track of a subset of the data. But they have ways of keeping in sync. And that's what the next part is about. So how does this database keep in sync? Because if I put some data here and some data there and some data there, how do I know which data to look at? And what about if one node goes down, I need backups, and I need backups of backups and so on. And that's actually the idea of replication, of course, right? So within these distributed databases, there's this idea of consensus, which is algorithms or protocols to maintain consistency among the databases at the log level. And these algorithms, they go back actually to the 60s when the ARPANET was being worked on and so on. And a lot of theory was developed in the 80s and 90s. Most notably, probably the first major result was in 1982 with Leslie Lamport and his colleagues at Microsoft, where they came up with the concept of Byzantine fault-tolerant behavior and a theoretical solution to it. And Byzantine basically means not only keeping things consistent, but also handling when you have malicious actors, people that are agents that are trying to break the system. And so that came along and it was kind of ignored. This was still the early 80s. There wasn't a lot of big networks. And then in 1990, Lamport and his colleagues came up with this idea, which they called Paxos, submitted it for publication. It got rejected, so they just let it gather dust. It finally got published 8 years later when the world kind of realized, hey, maybe we should publish this again. And it was accepted. It was actually a really horribly written paper. But since then, this paper, Paxos, has become very, very famous. A, as really hard to understand, which isn't quite true, but also as an important result for also consistency among databases. And so what Paxos is basically a protocol that's provably correct to maintain consistency among the different nodes in a database, and you can implement it. And that's where a lot of the implementations of the early 2000s came from. Things like Apache Zookeeper, et cetera, were originally based on Paxos. Turns out that to implement them, there was some deviations from Paxos, but the general idea is held true. So there's this idea of consensus. It's been around a long time, and it's what powers things like Cassandra. So going back to the blockchain world, right? So blockchains are a revolution, or they can revolutionize stuff, but scale is really, really an issue. So people have been talking about, okay, well, let's just scale up the blockchain. Let's just scale up the blockchain. Well, a lot of you guys have done work in machine learning. Have you ever tried taking some sort of algorithm, your toy algorithm that you played with, say some genetic programming, and said, okay, great, I'm working on 10 variables. Now all I need to do is scale up my genetic programming and make it work on 10,000. Guess what? It doesn't fly, right? It never, ever flies. Basically, as you have probably seen with the research from Norvig and others, as you actually go to higher and higher scales, the algorithms change, and they tend to get much simpler and much simpler and much simpler, right? You have to keep the same inputs, you have to keep the same outputs, you want to maintain the same behavior, but you have to let go of your pet algorithm, right? It's really about the results. So trying to take an existing blockchain idea and scaling it up, well, maybe you'll get 10x if you're lucky, or 50x if you're really good. And that's actually what kind of everyone has been doing. Major debates in the year 2015 over this. Lots of tears. But that's what everyone is doing. We started asking the question, what if you, instead of big data-fy blockchains, what if you blockchainify big data? So what if you start with something that naturally scales and give it characteristics that blockchains have, right? So start with that. And there's way more history of research in big data, thanks to the database research going back decades. But then the one question is, how do you blockchainify this? What does that mean, right? So a lot of people will have big debates about what blockchain means, and fortunately, we've been doing blockchain stuff since before it was cool. It's very uncool for a long time. And I don't care about cool or not, I just care about what's interesting to me. So I'm gonna give you some definitions leading towards working definition for blockchainify and blockchain. So first of all, decentralization. Decentralization simply means no single entity owns the controls. And this is really useful to disambiguate from the word distributed. So distributed means the resources are shared among more than one machine, whether it's processing resources, storage resources, and so on. So there's still a lot of confusion in the community. People use the word distributed ledger, for example, to mean actually decentralized ledger. So there's a lot of miscommunication. But this is actually a good practical definition. So you can have centralized distributed databases, and that's actually what we have with the Cassandra implementations that Netflix has, et cetera. But we can also have decentralized databases, where no single entity owns or controls those databases. Immutability. This is the idea that it's more tamper resistant than usual. Nothing is perfectly immutable, right? We already have logging databases. We already have automatic storage to magnetic tape drives, et cetera. And so there's already degrees of immutability that we have, but there's things that we can do to make it even harder to remove what was written before, right? So we can do things like hashes of hashes of hashes, sort of like a snail shell getting larger and larger and larger. And this is actually one of the newer ideas that blockchains bring. Although actually even that research goes back to the early 90s, literature on timestamping. So Satoshi didn't invent very much. A lot of people would claim that he invented everything, and he does a lot of other magical things, but there's really not a lot of magic. It's actually just good engineering with decades of history. So that's immutability. There's another really cool idea, and that is assets. And so imagine if you have some sort of storage medium where assets can truly live on that storage medium. Now, for that to be the case, no single entity can own or control that medium, because otherwise they would be owning the asset, right? So as a prerequisite, you really need the decentralization and also the ability that those assets couldn't be arbitrarily deleted. You need the immutability. But once you have that, then you can have assets that live on there. You can issue assets, you can transfer assets, and so on. And you can define an asset as, I own the asset if I have the private key to that asset, which is essentially the password. So I enter the password, I can transfer it to my buddy. Then he owns the asset, he can transfer it, and so on, and so on, and so on. So that's assets. And these three characteristics together, decentralization, immutability, and assets, this is really what people talk about as the major benefits they get when they have a blockchain as a storage medium, as a noun. There is a more narrow definition of blockchain that goes back to the early 90s, and that's literally this chain of hashes, the timestamping literature, et cetera. But that's really pretty narrow, and no one really, even though you could argue that that's the real definition, no one really bothers because there's so much more value. So blockchain, the noun, is some sort of storage medium that has decentralization, immutability, and assets. Then the adjective is simply the collection of these three sub-adjectives. So blockchain, the adjective, means decentralized, immutable, and assets. That's it. So that's the working definition of blockchain. Then what we can do is we can say, let's give these attributes to an existing big data database, to an existing distributed data database. So this is how you do it. This is how you blockchainify big data. First of all, the key thing, this is about scale and speed. So you have to say, let's retain the performance of this big data database. So you've got some sort of Paxos derivative, whether it's Raft or something else, that's solving order. You get out of the way of that. You let it keep solving order. You don't need to try to solve order on top. And what that is doing is it's actually naturally building this log of all the transactions. And once you have that log, all the other information can be kind of built on top in this hierarchical fashion. So you let the database keep doing that, right? It's all about order. And then once you make sure, so that's sort of a constraint as you're doing this, and then you add in these characteristics. Decentralization. So obviously with decentralized databases, sorry, with distributed databases, you've got 10 nodes, 50 nodes, whatever. What if you say, okay, each of those nodes, you have a piece of control, and collective all of you guys have all the control together, right? But that's it. So, and imagine if you say each node gets one vote. Simple enough, right? And it's actually as simple as that in a sort of theoretical fashion. You call this a federation, and then you say, okay, for any transaction to go through, all the a majority of nodes have to say yes, or for a transaction to get rejected, a majority have to say no. And they just say no to the transaction, and that's it. Now, if you want, you can actually say, okay, it turns out you can optimize this, and you can say, instead of doing one transaction at a time, let's vote on 1,000 at a time. And that's actually faster, and you group these 1,000 transactions into a block. And that's where the idea of a blockchain comes in, because you also have the hashes on the blocks. So you have decentralization via federation of nodes. You have immutability via simply hashes on blocks and a few other related ideas. And then for assets, it's basically saying, making it really easy to register an asset, making it really easy to transfer an asset, and then you have digital signatures on this. So the digital signature is basically only myself, only I can sign this, and then I'm done. So really, like at the core level, it's really these three things, kind of simple conceptually, and of course, so in the real world, it takes effort to get there. And I'll just describe a bit more of the architecture. So overall in the system, this is what BigchainDB looks like. We actually built on top of an existing distributed database. We actually looked at quite a few, benchmarked quite a few, including MongoDB, Cassandra, Elasticsearch, and so on. And the first thing we noticed was they're all wildly better scaling than any blockchain out there. And we knew that, not surprising. But then we actually filtered down to one of the main characteristics, and that was how good is the change feed mechanism? So a change feed as in, instead of having to poll the nodes to see what happened, how good they are telling you about what's happening in real time. And RethinkDB is really designed for that from the bottom up. So, so we chose RethinkDB. It's a JSON-style document store built in C++. And in the architecture here, in the very, very center, you see there's 3 RethinkDB nodes. That's the R's, probably obvious. And then wrapping each of those nodes is a BigchainDB server node. And that's what we see here. So there's a BigchainDB server node for each of those. And then there's the client side, whether it's Alice or Bob or whatever. And Alice and Bob, they're running some client-side software too. That's quite straightforward. So that's roughly speaking the architecture. One constraint we gave ourselves, and this was related to letting the core database, in our case RethinkDB, the constraint we said was don't add any new communication mechanisms beyond what RethinkDB had, because it already has its way of communicating. So if I wanted node 1 to talk to node 2, then it has to be actually via storage inside RethinkDB itself. And what that looked like was the following, 2 tables. So one table for incoming transactions, and another table for the actual set of information that's being stored permanently, this sort of blockchain, the set of transactions about who owns what, et cetera, et cetera, et cetera. So the incoming transactions come in on the left, and they're immediately deterministically assigned to a given node to handle. And they're grouped into blocks as they come along, and once there's enough transactions for a given block, for a given node, he writes that block to the table on the right. This is all within one RethinkDB instance. And other nodes are also trying to write to there. And here's a key thing. When you write to the table on the right, so WRITE, writing to the table on the R, you guys know what I mean. Anyway, when you write to it, you let the raft algorithm, the consensus algorithm of RethinkDB, sort out the order. We don't impose an order. We let the underlying consensus algorithm solve it. So basically, things get written on the right. They're grouped together. And then once they're written, we actually vote after the fact, because we found that writing was a bottleneck. So we write, and then after the fact, we're like, okay, this whole group of transactions here, are they good? Yes, no, yes. And each node votes, and then once the majority has said yes or a majority has said no, you know whether or not that block is good or not. So it's as simple as that. It feels very, very simple, and that's because, as you guys have probably seen in your own experiences, when you do stuff at scale, it's really the simplest algorithms that emerge, and that's really what you have to kind of aim for. and you have to constrain yourself to just the simple and the elegant. Now, obviously, there's a lot of ways to do things that are simple still, right? It's still a big design space for simple, but this is what emerged here. So we were benchmarking this, and the very first thing we did, well, as we iterated on this, we said, okay, if we design the algorithm just right, then we can actually get away with benchmarking just RethinkDB as a first cut. Because everything else we're kind of getting out of the way. So we designed the algorithm where the rest of the algorithm got out of the way, and we could focus on just seeing how far can RethinkDB scale. So in this set of benchmarks here, what we did was we started with just one node, and then we added a second, a third, all the way up to 32 nodes. And then we saw how the throughput, the number of writes per second increased. And you can see as it goes from 1 to 32 nodes, the writes per second goes past 1 million, basically. And this is actually blocks of 1,000 transactions were, and then so it's 1,000 writes per second times 1,000 transactions per second, basically speaking. So what we could, and then this plot can translate into just a simpler plot, which is very much like the Cassandra plot before. So the x-axis is number of nodes, the y-axis is number of writes per second. And we can see that we get more than 1 million writes per second this way. And this is on RethinkDB, knowing that if we have RethinkDB going really, really fast, then everything else, all the algorithms around it, we've designed them where they work too. And we'll be releasing benchmarks in that shortly as well. So basically, interestingly enough too, as we were working on this, we found probably 4, 5, 6 bugs in RethinkDB. And we worked with the team at RethinkDB to help resolve those bugs. And often they made a difference of like 2x or 4x to the speed. So this actually improved the speed of the RethinkDB database. We wrote a paper about this in great detail. Some people call it a book because it's about 70 pages, but it's really an easy read. And by the way, I will get into all the Python stuff in a bit here, but to kind of summarize a bit here on sort of what is it that we built, right? One way of thinking about it is trying to bring together the best of two worlds, the world of big data, distributed databases, and the world of blockchains. So what blockchains bring to the table is this concept of immutability, this concept of decentralized control, and this concept of assets. And then from the big data world, it's things like, it's basically scalability, right? So throughput, low latency, high capacity, permissioning system, querying, all this sort of thing. And so, if you're coming from the big data world and you ask yourself, well, why would I ever care about using a blockchain or a blockchain database? It basically comes down to, is there value in immutability? Or is there value in decentralized control? Or is there value in assets? So for example, if you are a bunch of, if you're the music labels, right? And you're not very happy with how Apple's behaving, they're taking their 30% cut, yet you don't have your own way of working together with the other music industry labels. What if you actually had a way to join forces, have a database that you don't control, but none of your competitors can control either, but collectively you own and control that, right? They tried doing this a few years ago. They failed because they couldn't agree on a technology because it came down to one of them controlling it. Blockchains actually allow them to collectively have a technology that they only control collectively. So that's one example. In general, this idea of consortium databases is actually a pretty powerful concept. And also, we kind of view it as, back in the day, there was SQL databases, relational databases. Then along came the NoSQL databases, which offered scale, which offered ideas of aggregation and so on, or the graph capabilities. And this is sort of a new type of database that's really emerging, this new blue ocean database. And it's really, a blockchain database that's immutable, decentralized assets. To give you a feel of how people use this, Everledger is one of our users, customers, and they're doing this for diamonds. So basically, if you go and buy a diamond from some dude in the street, how do you know it's not a blood diamond? How do you know it didn't come from child labor, right? How do you know it isn't stolen? What if there was a registry for that diamond that was being managed by all the major certification houses of the world and the insurance companies and the mines, et cetera? So this is exactly what Everledger is doing. And so it's the diamond supply chain. The diamond industry is about an $80 billion industry. It's been estimated to have 40% fraud, and it's been totally opaque so that no one was detecting the fraud. We actually worked with Everledger. We swallowed all of their diamonds that they had so far, as well as some eBay data. And so we had almost 1 million diamonds, and we swallowed a month's worth of eBay USA data. And we actually did machine learning analytics, reconciling the data from the certification houses, 5 certification houses which would never talk to each other before. We reconciled that with the eBay USA data and found 7% fraud rate. That works out to $750 million a year worth of diamonds. This is an example of the value of blockchain. So basically, $750 million of fraud that was going to criminals. Now it's being prevented thanks to Everledger and BigchainDB. Another example is energy deregulation. So RWE, biggest energy provider in Germany, they're being asked, the laws in Germany and Europe are getting deregulated, right? So if you have energy provider A, some guy with a solar farm, another person with a wind farm, how do they sell that to the grid? Who's managing? Do you want some centralized controller? Wouldn't it be cool if there was no centralized controller and instead every single node could talk to every other node and there is some way where markets emerge, et cetera? So this is actually the promise of blockchain technology, and there's a whole bunch of initiatives around this working on it. So we're working with RWE as well in general to help manage the dollar flow in energy regulation. Another example is in the world of health. So if I'm a doctor in London and Bayer comes to me or some other big pharma and says, hey, I'm going to fly you to Hawaii for 2 weeks for this awesome conference. All you need to do is buy my drugs for the next 2 years or subscribe to my medical journals for the next 2 years. And the doctor's like, well, yeah, okay. And how do you know when it's legitimate versus not, right? So it turns out that what the UK government did was they actually created a law called the Sunshine Act. And every time dollars flow from hospitals in the UK to any of the big pharma or any of the big scientific publishers like Springer, et cetera, that has to be transparent. Perfect use case for blockchains. Blockchains are transparency engines. No one owns or controls it. So we're working with Tangent 90, which is a bunch of experts from the field, to basically shine a light on the flow of dollars among the UK medical professionals, the big 20 pharma, and the publishing industry. One final example. This is overall, the company I work for is called Ascribe. And we started out, I talked about this last year, with IP in the blockchain. We still do this, right? We had a talk earlier today from Ryan, who was actually talking about 3D IP, and it's very related to this overall challenge. So if I'm an artist, I create some digital art. How do I prove that I'm the owner? When I sell it to someone else, how do they know that it's me? And blockchain technology can help here. So Ascribe.io, we're moving very quickly towards using BigchainDB as well for that. And overall, the art industry itself, digital plus physical, is a $64 billion industry. Obviously, the copyright industry itself overall is, hundreds of billions. So Python. So if you want to try out BigchainDB, it's actually not much different than using other databases. We've gone out of our way. It's not like trying to use. If any of you have ever tried to use Bitcoin daemon or one of those, it's like this nightmare. It's just horrible, horrible. So we've gone out of our way to make this really simple. So off of BigchainDB.com, if you scroll down from the top, we have basically some links to just get a very quick start. So the very first thing is, obviously, we've open sourced it. It's AGPL. It's on GitHub. And the link to GitHub, you'll see everything there, all of our tickets, all that sort of thing. We've also gone out of our way to document this really well. So we're using read the docs. And I'll give an example. I'll drill in on that in a second, basically, to get going and playing with BigchainDB. And so installing it, we're also within the PyPy repository, so you can just do a simple pip install BigchainDB, and you're good to go. So thanks, Sylvain. We have a few of our local Python experts in Ascribe, so this helped keep things simple that way. So I'm just going to give an example of the usage of this. BigchainDB itself is all written in Python. RethinkDB is in C++, so we've got C++ at the very core and then Python. And I'm sure a lot of you guys have this experience. You shouldn't be trying to write things prematurely optimized in some harder, slower language like C or something. Write it in Python, and then anywhere you have bottlenecks, that's where you start to optimize with the algorithms first, and then if you really need, you can optimize in some other language. So this is our path as well. So basically, in this case, once you have BigchainDB installed, you also have to install RethinkDB, which is also simple. Then you get RethinkDB going. You run the configuration of BigchainDB. You get it going to start. So the BigchainDB daemon is running. And each one of the server nodes would run this. We have actually scripts to deploy clusters to AWS and so on. And then in a new terminal, start up new terminal, get Python going there. And I'm just going to give an example of running a client here. So you first of all import BigChain, and then you say B equals BigChain, which is now you've got this object of the class BigChain. And now I'm just going to show how you can create a digital asset and transfer it. So it's just dead simple, right? First of all, you import this crypto library from BigchainDB, and then you generate a key pair, which is a public key and a private key. And this is just an example of how you get a key pair. Of course, in a real world scenario, you don't have to do that. You would have it from something else. You have some sort of digital asset payload. So this is the, you can have a message, or you can have something very detailed if you want. It's all JSON, so it's straightforward. Or Python dicts, which translate to JSON. And then you create a transaction, which is basically saying from who to who. In this case, you're saying I'm creating, so I'm doing a register, and then it's passing in the payload. And then, in a crucial thing here, you have to sign the transaction. And this is basically saying, you sign it with your private key. And this is basically proving that it was me who is doing the transaction. So when I write to the BigchainDB, the world can see that it was me because they can verify against my public key. And so after the signing, then the step is just simply to write it. And writing it will actually write it to the BigchainDB server-side instances. And of course, you can retrieve that just like any database. So you know what this is, it looks, acts, feels like a database, right? So this is probably super dull to you guys. It's like, duh, of course this is a database. But that's the thing. This is also a blockchain. It's a blockchain database, right? So the whole point is that blockchains can look, can act, can feel like databases. So here you say, what does the transaction look like? You retrieve it. And it's got a few fields, basically an ID, and then the transaction information. And the transaction information has three main subcomponents: the conditions, which is sort of like the inputs, the data, which is the payload, and you can have a lot of things like metadata, like artist name, et cetera, in there, and then fulfillments, which is sort of like the outputs. And I won't get into great details here, but that's roughly speaking how it is. Once you've got that asset, that digital asset created, you can transfer it. So here at the very top, I'm generating a key pair for some user number 2. Then I'm creating a transfer transaction, and that's basically between user 1 and user 2. And then of course I have to sign it. And if I'm not the owner of this, then the signing isn't going to be very helpful, of course. So I have the previous creation, obviously I signed that one. So I sign it, and then the final thing is I write the transaction, and that goes off to the database. Now if I neglected to sign this, or if I signed it with the wrong private key, then when it goes to the database, it would get checked by the database nodes, they vote, and they say, ah, no good, right? And it would get kicked out. And actually, that's what I just described. The not signing is one of a broader set of conditions. What if I created that asset and I sent it to Sylvain, and then also I sent it 2 minutes later to Ryan, right? Well, Sylvain will get it, but it will complain when I try to send it to Ryan. It'll say, hey, you've got a double spend. And that's what I'm showing here as an example. Basically, I create the transaction, I send it I send it to a new person, and it, of course, it complains, and it gives me an error message. So in starting to wrap up here, this is the second last slide. On the left, I talk about the centralized cloud stack that we have today, right? In the case of Amazon, we've got EC2 for processing. We've got a file system or file systems like S3 and all this, and then a whole variety of databases, whether they're SQL or NoSQL or whatever. And then the applications running on top on the web or on mobile. Now, the world is shifting. This is centralized stuff is going to be around for a while, probably quite a long time. But we're moving towards something that's much more decentralized as well. So it's sort of this vision of Internet 3.0. So you can take baby steps, which is pretty cool. So a lot of the value is in things like registries, where you retain your full stack that's fully centralized, except for the one thing. You add one new database. The new database is BigchainDB. So maybe you keep around your MySQL database and your MongoDB database, but you also are using this other database, this registry, that's out there that you don't own or control, that no one owns or controls, but that a set of people collectively own and control. And that's what the middle is. So it's partly decentralized. And that's actually the stack that Ascribe has. So we've got centralized servers running Django on Heroku, and we've got, we're using S3. So the application itself, the Ascribe web app, is partly decentralized. But what we're moving towards is this world where there are applications out there that are fully decentralized, decentralized apps, or dApps for short, or even apps that go beyond the idea of sort of even an application. They're more like an organization, and that's the idea of decentralized autonomous organizations, or DAOs, right? So that's the thing on the far right, on the top, and there's just an explosion of these. And what's powering them is three things. Ethereum, which you can view as scripts that are running, decentralized processing that are running that no one owns or controls. And there's a whole stack and ecosystem around Ethereum, platforms, et cetera. And then under the hood, Ethereum hasn't traditionally had much for storage media. So that's where there's a decentralized file system that's been emerging. That's IPFS, Interplanetary File System. Super cool. I encourage you guys to check it out too. And the database, which is actually what we've been building, what I presented today to you, BigchainDB. There's public versions of all of these too, private and public. So with BigchainDB, we'll be actually more fully announcing a public version of BigchainDB in a couple weeks. But also in general, you can roll this for private networks or public networks. So we're moving towards a much more decentralized world, sort of an Internet 3.0. And so I'll wrap up. Basically, BigchainDB, it's a blockchain database. It's scalable, and of course, it's in Python. So if you want more information, obviously feel free, come talk to me. Go to BigchainDB.com, read the docs to get started, check out GitHub. And we have a mascot, his name is Wrigley. He's a moose. He's from Saskatchewan, Canada, like me. And that's all. I'll wrap up there. Thank you very much.
Thank you, Trent. Thank you for a stunning presentation. Questions? I would expect tons of questions. We have only 3 minutes.
Hello, thanks for the presentation. It's an amazing project. Something that I see in blockchain and I don't understand how it works here is that you mentioned that validation is through some kind of voting system, and I understand that the nodes are the entities that vote. So what stops me from spinning up a lot of nodes to get a lot of votes, for example, or abusing the system that way?
Yeah, so that actually, by the way, is called a Sybil attack. And that's a problem when you have a fully open network, when you have unrestricted membership. So how Bitcoin solves that is saying your amount you vote is based on how much electricity you spend. Yeah. How we do it here actually is with a federation where it's a list of public keys. So basically, if I'm creating a network for the medical community, I'll just have the list of the 20 hospitals that I want running nodes. And that's it, right? And then you can add nodes and remove nodes on the fly. And basically the adding and removing is the existing nodes, they vote on that. When we roll out the public version of BigchainDB, it will also be based on this concept. So we've been actually working on gathering together a lot of organizations that really care about the future of the internet and the past of the internet. And collectively, they will form a bunch of nodes. And then to add more nodes, they collectively vote. To remove nodes, they vote. So it's actually a pretty good workaround. You don't need to get fancy with crypto economics, with crypto coins or anything like this. It's just a much more pragmatic solution. And it also happens to scale a lot better.
But at some point, there's this centralized organization, perhaps democratic, that decides who enters and who doesn't. No, you don't need it, right?
You have these 19 nodes, and basically one entity can propose, hey, I'm going to propose to add this node here, and then all the other nodes, they vote, right? People can sit down and decide whether they come in or not, right? So you don't need an entity, actually, a centralized entity. It's just like the DAO right now, right? The DAO it's this code that's out there running, and you're going to get a vote proportional to how much money you put in, right? So if you put in $10 million, you get less than 10% of a vote. Isn't that nice? Anyway.
See, my question regarding here is, I heard about Bitcoin blockchains, but there will be a validator. They call it as miners, correct? They will validate each and every transactions, and they will push the block to the blockchain DB.
That's correct. Yeah, that's how Bitcoin works. So basically, there's these nodes that they validate that the blocks are okay. And then in the act of, you spend electricity in order to get the chance to be elected, randomly, based on how much electricity you spend. And if you get elected, if you get chosen in that round, you win the lottery, then you happen to validate that 10 minutes worth. And then that's it. That's how that block gets validated. How we work is we say, ignore all that extra complexity about spending electricity, et cetera, and instead, the validation is done by these existing nodes. So there's no mining per se, there's no cryptocurrencies being created. The reward is extrinsic. Basically, the participants in the system that are doing the validation, they have a collective interest in seeing this network run and survive.
So I have a related question on the incentives. If it works, but it doesn't work perfectly and it would benefit from an upgrade, how do you have a tragedy of the commons situation or something like this? Do you have like trade-offs to vote who's gonna spend money to run more nodes or stuff like that?
Yeah, so in general, with this sort of setup, you're probably going to have 15, 25, 35 nodes. You're not going to have 5,000, right? And usually it's going to be a bunch of people that you probably know, like they're all in your trade organization, or they're all the people in some supply chain ecosystem, et cetera. And they're all going to be incentivized to have the most recent version of the software, right? If they don't, if it happens to be a speed optimization, maybe they won't bother upgrading, right? In the world of blockchains, this is called a soft fork versus a hard fork. So a soft fork means you upgrade, but it doesn't affect the protocol at all. A hard fork means everyone really has to upgrade or not be going on. In the world of databases, you think about, you're running a database live, and then you have data live on that. You do a migration of the schema, right? A schema migrate. So this is actually a much healthier way of thinking about it, rather than hard forks and soft forks. It's more like, okay, having scheduled maintenance upgrades and so on, where everyone agrees, and if they don't agree, maybe it will get stuck in some old version, and that's how it works. But overall, governance, the general approach to governance is basically this majority idea, right? Whether it's adding or removing members, whether it's upgrading or not, et cetera, right? So if you consistently don't upgrade, then you can get removed as a node, and another node will come in that actually does properly upgrade.
Yeah, great talk, Trent. Yeah, so this leads me to my question, which is majority votes. Have you thought about something else to decide rather than a majority? There's all kinds of ways to reach consensus, I guess.
Yeah, I mean, there's a lot of ideas out there. That's actually a pretty broad design space that you can have. But majority is a pretty good starting point, right? There's a lot of other things. Even in the world of traditional blockchains, right? With Bitcoin, there's this idea of the longest chain rule. So whichever chain of blocks is the longest, that's what the ground truth is. With Ethereum, there's something called the ghost protocol. You can have 2/3 votes, you get a majority votes, you can have things weighted. But majority is actually pretty good. It also ties in nicely with theory from Byzantine fault tolerance of the 2f+1, 3f+1. So there's other reasons for kind of sticking with something simple like this for sort of theoretical reasons.
I would like to stop here. Thank you very much one more time.